So we're now looking at chapter 7.3. We're going to start talking about sampling distributions in the central limit theorem. In this particular chapter, we're moving directly from probability to statistics again. And so this is our transition. Our first objective is to construct the sampling distribution of a sample mean. In real situations, statistical studies involve sampling several individuals, then computing numerical summaries of the sample. Most often, the sample mean, x bar, is computed. So in this example, we have a population, and inside the population we have various samples that have been taken, and there's an x bar associated with each one of those samples. If several samples are drawn from a population, they are likely to have different values for x bar, because the value of x bar varies each time a sample is drawn. X bar is a random variable. For each value of the random variable x bar, we can compute a probability. The probability distribution of x bar is called the sampling distribution of x bar. Tetrahedral dice are shaped like a pyramid with 4 faces. Each face corresponds to a number between 1 and 4. Tossing a tetrahedral dice is like sampling a value from a population of 1, 2, 3, 4. We can easily find the population mean, which is mu equals 2.5, and the population standard deviation. We saw how to do this from a population probability distribution of the population. If a tetrahedral die is tossed 3 times, the sequence of the 3 numbers observed is a sample size 3 drawn with replacement. The table displays all possible sample size 3 and the sample mean x bar. So here's our table. And so, for example, if we get 1, 1, 1, we sum them up, which would be 3. We divide it by 3, we get x bar to be 1, and so forth. The mean value of x bar is mu 2.5, and the standard deviation of all values of x bar is sigma x bar, which is 0.6455. Next, we're going to compare these values to the population mean, 2.5, and the population standard deviation of 1.118. So in the previous table, the mean sampling distribution is mu x bar, which equals 2.5, which is the same as the mean of the population, mu equals 2.5. This relation always holds, that the population mean is equal to the sampling distribution mean. The mean of the sampling distribution is denoted by mu x bar and equals the mean of the population. The standard deviation of the sampling distribution, sigma x bar, is 0.6455, which is less than the population standard deviation of 1.118. It is not immediately obvious that these two quantities are related, but if we divide the square root of the sample size, we get the same answer. Note that sigma x bar is equal to 0.6455, and recall again that the sample size is 3. So this suggests that sigma x bar is equal to sigma divided by the square root of n. We call this the standard error. So here's an example of the sampling distribution. Among students at a certain college, the mean number of hours of television watched per week is mu equals 10.5 hours, and the standard deviation is equal to 3.6 hours. A simple random sample of 16 students is chosen for a study of viewing habits. Let x bar be the mean number of hours of TV watched by the sampled students. Find the mean, mu x bar, and the standard deviation of sigma x bar. Well, the mean is nothing more than the population mean, which is 10.5, and the sample standard deviation, n equals 16. Therefore, the standard deviation is sigma x bar, which is sigma over square root of n, which is 3.6 divided by the square root of 16, which is 0.9. So our standard error, therefore, in this particular case is 0.9. Now, consider again the tetrahedral die example. The sampling distribution for x bar can be determined from the table of all possible values of x bar for a sample size of 3. The probability that a sample mean is 1, for example, is 1 divided by 64, or 0.015625, because out of the 64 possible samples, only one has a sample mean equal to 1. Similarly, the probability that x bar is equal to 1.33 is 3 out of 64, or 0.046875. Because there are 3 samples whose sample mean is 1.33. The probability distribution is follows. This is x bar, and this is the probability of x bar. Now we have a probability distribution. This, of course, is now called our sampling distribution. So in this slide, I want to go over just a few things. This particular distribution is the population distribution for x, where x can take on the value of 1, 2, 3, 4 for the tetrahedral die example. For example, when we roll the die, each number has the same chance of appearing, 1/4. So you can see we have what we call a uniform distribution for our population. Now, the probability histogram in the bottom here is for the random variable x bar for the sampling distribution with a sample size 3 obtained from the sampling distribution on the previous slide. The probability histogram for the sampling distribution looks a lot like the normal curve, whereas the probability histogram for the population does not. Remarkably, it is true that for any population, if the sample size is large enough, the sampling mean will be approximately normally distributed. For a symmetric population, like the tetrahedral die population, the sample mean is approximately normally distributed, even for a small sample size of 3. So, if a population is skewed, a larger sample size is necessary for the sampling distribution of x bar to be approximately normal. Consider the following probability distribution. This is for a population, for the value of x, and now, not x bar, just x, sorry. Now below are the probability histograms for the sampling distribution x bars. So these are the various sampling distributions for x bars. So we went from the population. When we sample, we continue to sample from the population. Each time we sample, we can start getting the probability distribution, which is then for x bar, our sampling distribution. Below, the probability histograms for the sampling distribution for x bar for the sample size 3, 10, and 30. Note that the shapes of the distributions begin to approximate a normal curve as the sample size increases. The size of the sample needed to obtain approximate normality depends mostly on the skewness of the population. In practice, the sample size n greater than 30 is large enough. So here is our holy grail of statistics, the central limit theorem. The remarkable fact that the sampling distribution x bar is approximately normal for a large sample from any distribution, is part of one of the most used theorems in statistics, called the central limit theorem. So, this is what it says. Let x be the mean of a large n greater than 30 simple random sample from a population with mean mu and a standard deviation sigma. Then x bar has approximately normal distribution with mu x bar equals mu and a standard deviation of sigma x bar, which is sigma divided by the square root of n. The central limit applies for all populations. However, for symmetric populations, a smaller sample size may suffice. If the population itself is normal, the sample mean x bar will be normally distributed for any sample size. So here are some examples. An example of size 45 will be drawn from a population with mean mu equals 15 and a standard deviation of 3.5. Question is it appropriate to use the normal distribution to find probabilities for x bar? Yes, by the central limit theorem, since n is greater than 30, it has an approximately normal distribution. A sample size 8 will be drawn from a normal population with mean mu equals negative 60 and a standard deviation of sigma equals 5. Is it appropriate to use the normal distribution to find the probabilities for x bar? Well, in this case it is, because they tell you up front that it's being drawn from a normal population. Example 3. A sample size of 24 will be drawn from a population with mean mu equals 35 and a standard deviation of 1.2. Is it appropriate to use the normal distribution to find probabilities for x bar? The answer in this case is no. It doesn't say that the population is normal. And so in this particular case, because it is not greater than 30, we cannot use the central limit theorem. If we had the data, we can check to see what the skewness level is of the data set. Now we're going to use the central limit theorem to compute probabilities involving sample means. In our first example, we based the data on the U.S. Census. The mean age of a college student in 2011 was 25 years with a standard deviation of 9.5 years. A simple random sample of 125 students is drawn. What is the probability that the sample mean age of the students is greater than 26 years? Well, here's our probability statement. And here is our diagram. So this diagram is x bar. It's our sampling distribution. And now we say the sample size is 125, which is greater than 30. Therefore, we can use the normal curve. And so we know the following pieces of information. Mu is 25, and now we'll calculate the standard error, and we get 0.85. So now we're going to find the area under the normal curve. So again, we use our probability statement if we're doing this by hand, and since our table only looks at areas to the left of x bar, we will have to use the complement, which is 1 minus the probability that x bar is less than 26. And now we have to use the z transformation in order to use the z table. And in this case we do, and we find that from the z we get a probability of 0.8810 from the table. So we subtract 1 minus that, and we get 0.119. The other way we can do that is use the normal CDF, and there's the calculation. So we get close to the value of 0.119. Actually, it's probably about 0.12. So that the probability that the mean age of students is greater than 26 years old is approximately 0.1197. Here's example 2. Hereford cattle are one of the most popular breeds of cattle based on the data from the Hereford Cattle Society. The mean weight of a 1-year-old heifer bull is 1,135 pounds with a standard deviation of 97 pounds. Would it be unusual for the mean weight of 100 head of cattle be less than 1,100 pounds? So now we're not saying that the individual cow could be less than that. What we're saying is the mean value is less than that. So what we're saying is the probability that X bar is less than 1100, and that comes from drawing the sampling distribution. There it is, right? So we're looking at this area. We could do this by hand, which you probably should do, but we are going to use the normal CDF function. So the sample size is 100, which is greater than 30. We can therefore use the normal curve. We know what the mean value is, which is 1135, and the standard error is 9.7. So we plug it into the calculator under normal CDF, and we get a probability that is really very small, right? This probability is the probability that X bar is less than the mean value is less than 1100 is approximately equal to 0.000154. This number here is 10 to the minus 4. Okay, so this probability is less than 5%, so it would be unusual for the sample mean to be less than 1100. So in this chapter, you should know how to construct the sampling distribution of a sample mean. You need to know how to find the mean and standard deviation of a sample distribution of X bar. You have to understand the central limit theorem, and then how to use the central limit theorem to compute probabilities involving sample means. Now, that concludes our topic on quantitative variables, chapter 7.3, sampling distribution. 7.4 will be qualitative variables.